Welcome to the fourth week of the Powering Agriculture Mooc on Sustainable Energy for Food. Within that initiative, USAID, the governments of Sweden and Germany, as well as Duke Energy and OPIC, promote clean energy solutions in the agriculture and food sector. For the Mooc, the partners are cooperating with TH Köln, a university of applied science based in Cologne, Germany.
Hello, how are you doing? Today we are on the fourth week of our Mooc, and this week's broad content is about energy efficiency and sustainable energy use. In this lecture, I first talk about the general concept of energy efficiency. Then I will shortly brief you on energy auditing. Towards the end, we discuss about the sustainability of energy systems. So, what does efficiency mean? Efficiency of any system is the ratio of output to its input. This ratio expresses the ability of a process to utilize different inputs such as materials, energy, money, or human capital to produce a desired output. Indeed, efficiency of any system can be measured. For example, technical processes, economic activities, or even administrative processes. Now, let's talk about energy efficiency. The International Energy Agency defines the energy efficiency as a way of managing and restraining the growth in energy consumption. Something is more energy efficient if it delivers more services for the same energy input. You may call it a maximization strategy, or the same services for less energy input. You may call it again a minimization strategy. Let us now think of two different light bulbs, an incandescent bulb and a LED bulb. Both bulbs deliver the same brightness, let's say 1000 lumen. The conventional bulb needs about 100 watts, whereas the LED bulb needs only 20 watts to deliver the same brightness. In this example, as you can see, the incandescent bulb needs 5 times more energy to produce the same light effect compared to the LED. This example shows that a significant amount of energy can be saved using an energy efficient technology. And saving input energy also means saving money as well as reducing environmental impacts. But please be aware, energy efficiency is not the same with energy conservation. Energy conservation is reducing or avoiding a service in order to save energy. For example, when you turn off the light in your home, it is about energy conservation. But replacing an incandescent lamp with a LED lamp is about energy efficiency. Analysis of energy efficiency can be extended beyond the end users, such as to the energy production sector. Let's see an example of a coal power plant to produce electricity. Processes involved in such a power plant are coal mining, coal cleaning, crushing, and transportation to the power plant, coal combustion in the furnace, steam generation in boilers, steam turbine operation, electricity generation via generator, and electricity transmission via grids to the end user. As you can see, there are many intermediate steps in this power system. In each step, there is a certain form of energy loss. For example, a large amount of heat loss in a steam turbine or smaller electrical losses in a generator. Similar losses take place in other processes too, also in agro sector. Examples are cheese production from milk, biogas production from agricultural residue, fertilizer production, irrigation system, etc. If you analyze the energy consumption and losses of a complex process chain into its intermediate steps, we can identify the critical stages. This procedure is called energy auditing. An energy audit can be simple, just having a close look to the process and observing the area of energy losses. Or it can be a complex analysis where every single step of the process is examined, measured, and categorized according to its impact and replacement cost. Here is an example of a milled powder factory. Throughout the production process chain, multiple motors, refrigerators, heaters, and pumps are used. During an energy audit, we examine the efficiency of each component. In the next step, we look at the whole system. The factory uses a refrigerator at the beginning and a heater at the end of this process chain. The cooling process produces heat as a waste product, while the heater requires it as an input. By combining these two processes, we can reuse the waste energy and thereby increase the overall efficiency of the system. However, just being energy efficient does not necessarily mean the product or service we use is sustainable. Generally, the companies or end users are more concerned with the monetary loss or gain of implementing the energy efficiency measures. Environmental aspects are unfortunately of less priority in many cases. A holistic analysis of such process chains or a system can be a good instrument to support in decision making. This process is called sustainable life cycle assessment. What does the sustainability actually mean? In simple terms, it is the ability of a product or service to deliver its function in a better way than its substitute. We analyze the sustainable life cycle assessment of a product or a service at its three pillars. Environmental life cycle assessment, often called as LCA, life cycle costing, and social life cycle assessment. In these cases, the whole process chain analysis or so-called cradle-to-grave analysis is necessary. There are not yet international standards developed for the analysis of life cycle costing and social life cycle assessment. On the other hand, the procedure to carry out the environmental LCA is well developed. And there are two international standards for this, ISO 14040 and 14044. Environmental LCA is the compiling and evaluation of the inputs and outputs and the potential environmental impacts of a product system during a product's lifetime. Conducting the LCA involves 4 phases: goal and scope definition, inventory analysis, impact assessment, and interpretation. Goal and scope definition phase specifies the objectives and framework, system boundary, functional unit, and so on. Life cycle inventory phase includes data collection for all resources and materials input and products and emissions output. All flows are recorded and compiled in an inventory table. Life cycle impact assessment is about the calculation of potential environmental impacts. Results are summarized into impact categories. Examples are global warming potential, acidification potential, and so on. In interpretation phase, the results are checked and evaluated to see that they are consistent with the defined goal and scope. Analysis of sustainable LCA helps you answer questions such as whether to use coal or solar photovoltaics to generate 1 kilowatt-hour of electricity, or whether to buy milk in glass or plastic bottles or in paper packs. These and other interesting answers you can find in the reader. Now we are at the end of today's lecture. I hope you enjoyed the time with me. The quiz is waiting for you. Have a great time and see you in week 7.
Thank you for your attention. and see you next week.